Using what we worked on last lesson, the sample space diagram, we will learn the rules of combining probability. So if two things can happen, and we say whether or not they can happen together or not, it's important we understand the idea of independence. And what we mean in independent, if you actually look at the word in the dictionary, it means two things that are not linked. So independent for probability statement means that the two events, like flipping a coin and rolling a dice, are not connected in any way. If I get heads on the coin, it doesn't affect the chances of me getting a number on the dice in any form. And if I roll the dice, it doesn't affect whether or not I get heads or tails. So independent means they're not connected. The other word will come across, the mutually exclusive. We'll talk about it in a few. So you've got given a start to try and work out what's the probability of heads on a coin. There are two things that can happen, heads and tails. Head is one of them. On a standardized probability of a 2, well, it's 1 out of 6 items. Probability of a dice being even, that's 2, 4 and 6, is 3 out of 6, or a half. And we will be using simplified fractions today. Probability of two things, of a number being prime. Well, the prime numbers are 2, 3, 5. Okay, 1 is not prime, don't forget that one. So probability of prime is 3 over 6, or a half again. Probability of multiple of 3, well, there's 3 and 6, so that's 2 out of 6, which is 1/3. So we're now going to combine these questions and see what happens to the probabilities. We'll use the sample space diagram to solve the problem, and then we'll come back and fill them in. So let's look for the probability of a head and, that's the word and, probability of a head and prime. So head and prime. We know by using our table that heads is anything in this top row and prime are any of these three. So we know we've got 3 out of 12, which equals 1/4. Now, if we look at the two individual things altogether, the probability of a head is a half, and the probability of it being prime is a half. Now, there should mathematically be some way of combining these two fractions that will give us the same answer of 1/4. Okay, so we're going to look at it, think about what's happening. It might help if we look at the two unsimplified fractions even. So that's the probability of head, probability of prime. Now, think about your maths. How can we combine two numbers together? Well, we can add them. If I add a half to a half, that gives me 1. No, that's not going to work because it's not giving me 1/4. Subtract them, that gives me 0. It's not working. Multiply, well, multiplying fractions, multiply the numerators and the denominator. That seems to work. And if we try dividing our two fractions, a half divided by half or something divided by itself is 1. Or we can do change the divide into a flip. So a half divided by a half can be either 1 divided by 1 and 2 divided by 2, or take your fraction, flip it and multiply. Both of which gives us, top one gives me 1 over 1, bottom one gives me 2 over 2. So that both of those equate to 1. It's not a divide. Now, it might be something else, but at the moment, our best candidate is to multiply. If we look at our two fractions, which is mixed ones, 1 times 3 and 2 times 6 gives me 3 over 12. So that gives us our two ways we think will combine. Let's try another one. Let's try probability of a head and the multiple of 3. Sorry, let's go for a tail. And the answer is a multiple of 3. Well, tails, probability is a half. A multiple of 3 was 1/3, or a half times 2 out of 6. So if this multiplication works, we should get the right answer. Do the multiplication on the numerator, we get 1 over 6. If we do this bottom one, we get 2 over 12. 2 over 12 simplifies to 1 over 6, that's fine. Let's have a look at the tails. So we're looking for the tails and a multiple of 3. So it's got to be in this line. 1's not multiple of 3, 2's not multiple of 3, 3 is a multiple of 3, tail 6, multiple of 3. And we're not worried about the head. So we've now got 2 out of 6 things, which is my probability. And that's the basic form, is when you see and, you take your probabilities and multiply them with one proviso: they must be independent. And means multiply when independent. In some later parts of mathematics, you use this to prove that two probabilities are independent. You calculate the probability of a situation, you look at your two probabilities building up. If they obey the rule that you can multiply the two probabilities and you get the overall end probability, your conclusion is the two probabilities are independent. Right, let's try changing the other one now. And this is where it's quite important that you understand the word mutually exclusive. We'll do the first simple one. We're going to say, what's the probability of a tail 1 or tail 2? Let's scroll down. So probability of tail 1 or tail 2. I need to keep that on the screen if I can. Let's just move this down a little bit. So tail 1, we've got 1 out of 12. Probability of tail 2 is a 1 out of 12. Now, if you were to think about the situation in any way, it's a probability of them being tails and 1 or 2. Notice that in here we actually have ands. Each of these actually have a built-in and. So tail 1, what could we do with these? Well, we know the final result is 2/12. Because they're the two situations out of 12 that we're looking for. So how do I combine these probabilities to do them? Could be add. If I subtract, we get 0. If I multiply, I get 1 over 144. If I divide, I get 1 over 1. So that's not going to give me my probability 2/12. So the addition, we've got a common denominator of a 12th. 1 plus 1 on the numerator gives me the 2/12. So addition is an OR. But there's a problem. What if I was to ask something which goes across one row and one column? And this is where the idea of mutually exclusive. So we're now going to talk about mutually exclusive events. The situation we're going to look at is I'm going to give you a probability of there being a 1 or the probability of a head. Now, you might think from the previous one, okay, we're going to add our two fractions. Probability of a 1 is a 1 out of 6. Probability of a head is 1 out of 2. Turn them into have a common denominator, so they've both got a 6 on the denominator. So I've got 1 plus 3/6, which gives me 4 over 6, which is 2/3. Now let's check it using our sheet. We want a head, a 1. That's a 1, and that's a 1. Or a head, or the heads. Now, when we're using the sample space diagrams, we never double count a square. If you double count a square, you can wind up with probabilities more than 1. So if it's counted only once. So let's see what the final probability is. It's 1, 2, 3, 4, 5, 6, 7. The actual answer is 7 out of 12, which is close to this 4/6, but it's not the same. And the reason it's not the same is this double counting. That double count, this probability has actually done the double counting just by adding the two fractions. And that double counting breaks the rule of something being mutually exclusive. Mutually exclusive means that the two events don't overlap. So mutually exclusive and that means there's no overlap. Okay, so let's go and do last couple of questions. This time I'm going to do the questions using probability on 2 bags. We're going to calculate them first because we haven't got a sample space diagram. We will check it in a minute with the sample space diagram. So I want to know what's the probability of blue. We're going to take 1 from each bag, and the question is, what's the probability of 2 blue circles? So I can take probably 1 from this bag, 1 from this bag. I can't double dip into one bag. I have to take from bag A or bag B. So probability of 2 circles from bag A and B. So probability of bag A giving me a circle, a blue circle, and the probability of B giving me a circle, not a 0. Well, and is a multiplication. So the probability of A is 1 circle out of 5. And I'm going to multiply that by the 2 circles out of 4. Multiplying numerators gives me 2, multiplying denominators is 20. Simplify the fraction to 1/10. Okay, so that's our first calculation. Try the probability of a square from A and B is a circle. So the probability of A is a square, 2 greens out of 5. A is a square, and so and is a multiplier. Blue bag B is a circle, and that's 2 out of 4 again. 3 is a circle. Multiply through, I've got 2 times 2 is 4, 5 times 4 is 20, and that simplifies to 1/5. Let's do one more and then we'll check our answers. Probability of A being a triangle. Oh no, we'll do one more after this as well. Probability of A is a triangle or a square, and B being just a square. So probability of triangle or square in A, so triangles 1, 2, and 3, 4 is triangles and squares. So that's now 4 out of 5. And we multiply by the probability of a square, which is 1 out of 4. Simplify by multiplying through, so we do 4 times 1, and 5 times 4 is 20. Some of you would have done the early cancellation here, and you could have done it on this one as well. Yes, still works. I could do cancel the 2 4s, so I've got 1 times 1 and 5 times 1, which gives me 1/5, which is the simplified answer. There's just a benefit with probability of me haven't seen this denominator all the time through, and that's to do with when we look at our sample space, it's going to be easier to solve our solution problems. One last one. What's the probability of A being a circle, a square, and B being a pentagon? So how many squares were there in the first one? That's 2 out of 5. And how many pentagons are there in B? That's none out of 4. So we get 0 over 20, which is 0. It says that that cannot happen. Well, we have no pentagons anywhere, so clearly that can't happen. So I'm just going to pull over sample space so we can check our answers. Oops. Sorry. So I'll bring in the answer. And each place in each question, we can just count the squares that obey the rules. So A gives me a circle and B gives me a circle. First of all, let's look at the number of outcomes. Number of outcomes is, come on, give me the blue pen. So the number of outcomes where it's a blue circle. First of all, there's 20 outcomes, 5 columns of 4. So there's 20 numbers in here, or 20 solutions. This point is 2 circles. This is 2 circles. Circle and a triangle, circle and a square. So where did I get circle from A and a circle from B? In that place and that place. So that's 2 places out of 20, my probability here. A square in A and a circle in B. So square in A, circle in B is 1, 2, 3, 4. So that's 4 out of 20. Yep, same number we got over here. Triangle or square and squares. So triangle and squares are these 4 places, and only a square from B. So I've got 1, 2, 3, 4. So now we have 4 places out of 20 is my probability. And the last one, anywhere where there's a square in bag A and pentagon, well, there's none. So we get a probability of 0. That's using sample space diagrams, calculating probabilities using and or rules. Or you add the probabilities as long as they are mutually exclusive. The two things are not allowed to overlap in terms of double counting. You wouldn't be allowed to double count anything. Okay, so just be careful about counting squares twice, like this one. That's the thing to watch out for, and it's when you're doing OR. Next lesson, we'll probably look at tree diagrams, and they have a nice way of dealing with that problem. So